All right. So today we're talking about the history of the atom and the development of atomic theory and the modern atomic models that we use. So we're going to kind of go in order. So if you would, probably highlight things as I talk about them. Democritus, he was the Greek philosopher. He was the first one to say that everything is made of tiny particles called atomos. And so the way he did that, he took a piece of paper and he tore it in half. And then he tore that half in half, and then tore that in half. And he kept tearing the paper in half in little pieces until he got down to a piece that was so small that he could not divide it anymore. And he said that everything is made up of the same thing, and it's this indivisible particle that you can't divide any smaller. It's the smallest thing that you can get. And that's what everything is made of, and that particle is called an atom. Okay, atomos for Greek that's what atom means in Greek. And then shortly after that, like within the 50 years, Aristotle came along and said, no, that's wrong. Everything is not made of the same stuff. Everything is made of certain elements. And these elements, the ones that are found on Earth, are earth, wind, fire, and water. And he said that the stars are made up of something called aether, okay? And people believed that for like a couple thousand years. Like, it was pretty bad. Maybe not quite that long, but at least until Lavoisier came along and started making lists of elements and the development of alchemy, people thought Aristotle was pretty much right. He's completely wrong. That's not what things are made of. But fast forward a couple thousand years, and John Dalton shows up, and he's an English guy, meteorologist and chemist. He also taught school. He's a teacher, and he did some experiments in a lab, and he developed something called Dalton's atomic theory. Okay, so he said that atoms are tiny, solid, indivisible particles. So he kind of brought back what Democritus said, and he said that everything is made up of atoms, but not all atoms are alike. Okay, there's some stuff that's different about them. Okay, so he said all matter is made of atoms, and atoms are indivisible and indestructible. We now know that that's not necessarily true because of the development of nuclear weapons. Okay, specifically developed by nuclear chemistry and physics. So we now know that's not true, and we'll have a whole unit on that when we discuss what nuclear chemistry is. Then number 2, all atoms of a given element are identical in mass and properties. Okay, so we'll get to this in the notes, but we know that this is not true anymore because of the existence of isotopes. So these two stars, that means that these are no longer true. Okay, they were for the time, but now they're no longer completely true. Okay? All right, and then compounds are formed by a combination of 2 or more different kinds of atoms. And this is still true. Okay, and this led him to do some experiments with gases and come up with the law of multiple proportions. Okay, so when 2 elements combine and form more than one compound, the ratios of mass of one element in the first compound to its mass in the second compound can be expressed as ratios or whole numbers. So that's how we know that like all of water is made of 2 hydrogens and 1 oxygen. That's a very specific ratio, 2-to-1 ratio. That's how we got formulas, is based on the law of multiple proportions. And then he also said that chemical reactions are simply a rearrangement of atoms, and that is still also true if it's a chemical reaction. Not if it's a nuclear reaction, but if it's a chemical reaction, that is true. Okay? And Dalton proposed a model to go with it. This is called the billiard ball model. So think of it as like the white scratch ball, like when you're playing pool, it looks like the white scratch ball. Okay? It's just a sphere with nothing special in it. There's no particles. So this is before we knew about the existence of subatomic particles. We now know that that's not true. We have subatomic particles. So we know that this model is wrong now, but at the time, this was completely true. Okay? All right, so next page. All right, and so then we get to J.J. Thomson. Now, J.J. Thomson, Okay, he did an experiment with cathode ray tubes, okay, also called Crookes tubes. It's the same thing. And so he's credited with the discovery of the electron. So his experiments, I'm not going to tell you how the cathode ray tube works. It's not that important. But he basically shined a beam through and charged two plates, and they bent in the direction of the positive plate. So one of the beams bent. So he knew that there were negative particles in there. So he said there's also something positive in there, because the beam actually, it doesn't show it in this picture, but the beam actually split, and he could see that there's definitely something positive in there as well. So he decided that you have the negative particles, the electrons, embedded in a positive matrix, and he called his model the plum pudding model. And so then that kind of disproved the billiard ball model. Okay, then fast forward to the 1900s, and we have Ernest Rutherford. Okay, Ernest Rutherford, he developed a model using his gold foil experiment. He said, if I shine a beam of alpha particles into a super thin piece of gold foil, like so thin you can see through it, okay? If I shine that in there, then all the particles, according to Thomson's model, should go straight through. And so he put a detector on the other side to see that. What he noticed was they didn't all go straight through. So then he put a detector all around the room to see what's going to happen with this very thin piece of gold foil that he put in the middle of the room, right? And so what happened is particles ended up shooting off everywhere. And so he deduced there must be something dense that they're hitting and deflecting off of. So he decided that thing is called a nucleus, and that's where the positive is within an atom. It's right in the center in the nucleus. Okay, so he said the electrons are around, but the positive is right in the middle in the nucleus. And we call that either Rutherford's model or the nuclear model. Same thing. It's the same thing. Okay, and then along came Niels Bohr a little further into the 1900s. Niels Bohr comes along, and he developed something called the solar system model of the atom. So electrons circle in definite circular orbitals. So in this picture, N is the energy level. So the first energy level is energy level 1. That's the nucleus. So that's energy level 1. Second energy level is energy level 2. Third energy level is energy level 3. And it just keeps going. Okay? And he said, he did a lot of experiments with light that are kind of complicated, so we're not going to talk about that. But, and he discovered that, okay, these electrons, they can jump from level to level, but they're in a specific energy level. Okay? And then fast forward a little more, 1932, James Chadwick discovered the neutron. So this is after radioactivity was discovered. We discovered the neutron using some information about radiation. And with the discovery of the neutron, that's kind of where we said, oh, okay, so now we know why certain atoms are different because of the existence of isotopes. So that will come into play here in a minute. All right, and then fast forward a little more, and with all of those light experiments and things came something called the quantum mechanical model. So not only are the electrons in discrete energy levels, but within each energy level, you have orbitals. Orbitals are places where you are likely to find an electron, okay? Electrons are free to jump from orbital to orbital within an atom. And we're going to do a little bit of math associated with some of the light that's involved with that. Not a lot, but we'll do a little. But anyway, but that model, this is what we go by now. It's the quantum mechanical model. So Thomson disproved Dalton's model. Rutherford disproved Thomson's plum pudding model. Bohr disproved Rutherford's nuclear model. And the quantum model is a modification of the Bohr model. It kind of blends the two together. Okay? So the quantum mechanical model is what we go by now. All right. So what exactly is in an atom? Okay. So an atom has three what you call subatomic particles, okay? The average atom is very, very tiny. It's about an angstrom, okay? An angstrom is 10 to the negative 10th of a meter. That's really, really tiny. A proton is in the center in the nucleus. Its mass is about 1 atomic mass unit. So if you don't like AMU, like think of it as like a gram. Okay, it's just a weight, a measure that we use to measure mass or weight. So 1 atomic mass unit. Its charge is +1, and this is the symbol we typically use for protons. A neutron is also in the nucleus, weighs the same as a proton. So both of these are in the nucleus. Both of them weigh the same. But a neutron is neutral. Okay, and so we have a symbol. Electrons are in the electron cloud in the quantum mechanical model. Okay, and they are nearly massless. Okay, they are about 1/2000th of the mass of a proton or a neutron. So electrons do not contribute to the mass of the atom overall. They do contribute charge, though. They are negatively charged. Okay, so you have electrons. In a neutral atom, you would have the same number of protons as you would electrons. Okay, so more terminology. So the atomic number, this is the number of protons in an atom. Okay, the atomic number determines which element an atom is. So if you look at our periodic table on the wall, the atomic number are the blue numbers on the wall. Every time you take a test, you're going to face that periodic table. So you need to remember that the blue numbers are the atomic number. Now, if you notice, our periodic table is arranged in order of increasing atomic number. Okay? It didn't used to be that way. Okay, so let's turn the page. All right. Okay. Mass number is the number of protons plus the number of neutrons. Okay. We use something called a nuclide symbol, or a symbolic notation for a nuclide to determine how to notate it. But sometimes we will write with something, we'll write the element name and a hyphen, and then the number afterwards is the mass number. So for like lithium-7, okay, or Li7, lithium-7. So lithium-7, that would mean, okay, that lithium is atomic number 3, so the number of protons in there would be 3, and the number of neutrons, okay, would be the mass number, which is 7, minus the atomic number, which is 3, so that would give us 4 neutrons, okay? So really, literally, how you calculate the mass number is the number of protons plus the number of neutrons will equal the mass number, okay? Okay. Isotopes, these are atoms of the same element with different number of neutrons, okay? So like lithium-7 and lithium-8, these are called isotopes. They have the same atomic number. Their atomic number is still 3, but they have different mass numbers, so they have different numbers of neutrons. So lithium-7 would have 4 neutrons, but lithium-8 would have 5 neutrons, okay? So they weigh different amounts, but they're the same general element. Okay, so let's look at the example. So how many protons, neutrons, electrons are there in these 3 atoms, okay? So let's look at bromine-80, first of all, okay? So bromine-80, so the number of protons, well, we look at our atomic number for bromine, that's 35. So the number of protons is 35. If it's a neutral atom, then the number of electrons is also 35. So then the number of neutrons would be 80 minus 35. So what's 80 minus 35? Okay, so it should be 45. Okay, so why don't you try to do arsenic 75 and strontium 88 on your own, and you can look up when you're done. Okay, so hopefully you're pretty close to done. If not, pause the video for a second. I'm going to move on. I'm going to skip atomic mass for right now. Well, okay, I'll tell you that I'm not going to show you how to calculate it today. We'll do that next class. But atomic mass is the weighted average of the masses of an element's isotopes. Okay, so if you look at that on the periodic table, those are the red numbers. Now, because it's a weighted average of all of the isotopes, most of those numbers have a decimal and then some numbers after the decimal. The ones that don't have a number after the decimal, they just have a whole number. Those ones, there's only one isotope that exists or is found naturally. Okay, the bubble letters on the periodic table that's on the wall mean those elements are synthetic. They do not exist naturally found in nature. They have to be synthesized in a lab, which is probably why there's only one isotope of that particular element. Okay, so those are weighted averages. Mass number and atomic mass are not the same thing, and I'll show you how to calculate average atomic mass next class, and we'll do a lab. All right, let's look down here at ions and symbolic notation. So for ions, ions are atoms that have gained or lost electrons. Okay, if they lose electrons, they are cations. So if they lose electrons, they have more protons than they do electrons, so they're positively charged. Okay. Anions have gained electrons, so if they gain electrons, then they have more electrons than protons, so they are negatively charged. So cat's positive and anions are negative, okay? So it says determine the number of electrons and protons in each of these. So let's look at calcium. So calcium with a +2 charge, okay? So the number of protons in calcium never ever changes. You can't gain or lose protons. You can only gain or lose electrons. So the number of protons is 20. So if I have a +2 charge, that means that I have lost 2 electrons. So whatever the charge is, that's the opposite of what you do to the protons, and that's how many electrons you have. So if I have a +2 charge, I'm going to take 2 away from 20, and I would have 18 electrons. Okay, so why don't you try to figure that out for iodine with a -1 charge, and phosphorus and carbon. Okay, do that on your own and look up when you're done. Okay, hopefully you're finished. If you're not, pause the video and take a minute more and work. All right, and then we have symbolic notation for a nuclide. I like to call this the nuclide symbol because symbolic notation for a nuclide seems like a long thing to say. All right, so how do you do this? You write the atomic symbol, and then on the top right of that, you write the mass number. In the bottom left, you would write the atomic number. That's it. So let's say we wanted to do, the nuclide symbol for like uranium, 238. Okay, so the atomic symbol for that would be a big U. Okay, And then the mass number is 238. And the atomic number, according to the periodic table, is 92. That's it. That's all you do. Okay? So why don't you do let's do the nuclide symbol for nickel 59. So you do that on your own paper and then look up when you're done. Okay, and that's all, and that should probably get you through all of the homework.